Hello all, this is Dr. C. Padmini and I'm an assistant professor at Department of Electronics and Communication Engineering, and I'll be taking this course called Electronic Devices and Circuits, and this is the lecture 2. As we have discussed in lecture 1 that introduction to the semiconductor material and why semiconductor material is suitable for construction of electronic devices, and with the help of devices we are going to construct the circuits, and also we have gone through the construction of a basic electronic device called PN junction diode, and we are going to continue that particular topic of PN junction diode, and today's session, that is on lecture 2, we are going to take up PN junction diode, its operation by applying a proper biasing to it, and along with this we are going to see its volt ampere characteristics, which is plotted for both the biasing conditions under forward bias and reverse bias. And along with this we are going to take up how the effect of temperature is on the volt ampere characteristics, means how the voltage drop across a PN junction diode gets altered with respect to temperature, and also how the current gets altered with respect to temperature we are going to take up. So this is the lecture number 2. So let us start up with the PN junction diode, just recalling the basic things related to it. That is, as we have seen in the first lecture, a PN junction diode is a combination of P material, N material, and the fabrication steps also it is followed, with the help of which a junction is formed. On either sides of a junction, because of the ion accommodation, we are going to have a depletion layer that is formed. So we have seen how the property of a depletion layer has been exhibited. So now we shall just try to see how we are going to use it practically, this PN junction diode. And before going on to it, let us highlight onto the symbol of a PN junction diode. And basically this, as we have seen, it's a combination of two materials, anode and a cathode. So we're going to represent it with the two leads that are present, and the triangle shape, it indicates the direction of the majority carrier current. This is called as anode, or we also call it as P material, and the other line that is represents your cathode. As in the case of a vacuum tube, an anode collects all the electrons and cathode emits the electrons. Similarly, in the case of semiconductor material also, an N material emits the electrons and P will carry. So that's how the PN junction diode symbol has been represented. Anode is represented as A and cathode is represented as K. And this particular PN junction diode, we are going to see how it is going to work. And as we know, before going on to the working of it, by applying proper biasing, we shall just try to brief the structure that is present. Different biasing conditions we'll be going for. Okay, this is our structure and this is the junction that is formed. As we know, PN junction diode is lightly doped and the doping level is 1 in 10 power 13 pure atoms will be taken up. Either in the case of germanium or silicon, this is the standard rate used for the lightly doping. So PN junction, as in and when it is formed, as we know that P material has negatively charged ions. Because of the diffusion, neutral area will be formed. After that, the ion tend to get diffused. As they cannot cross the material, they get accommodated on either sides and forming your depletion layer. And this is how you have a depletion layer on either sides of a PN junction diode that is formed. And it exhibits certain potential. These are the leads of your anode and cathode, P and N material. And this, because of the charge accommodation on either sides, we see that a barrier potential called V gamma is exhibited. This barrier potential is the one which is making the majority carriers not to cross the junction. That is, holes which are present in your P material cannot cross the junction and move on because of the positive ions on the other side which get repelled. And also we have electrons as the majority carriers in N material which cannot cross the junction and enter into P because of the depletion layer. As it is working like a barrier for the majority carriers, we also call depletion layer as barrier potential. It is exhibiting certain potential, so it's called potential barrier. So this is how we have a basic PN junction diode and its structure that is present. Let us see the working of this by applying proper biasing. What I mean by actually a biasing is application of a DC source to any electronic device in order to see its operating conditions. That process we call it as biasing. Once again, it's application of a DC source to any PN junction diode or any semiconductor devices in order to see its operation is called as biasing. And depending on how we connect it, we call the biasing to be of two different types, forward bias and reverse bias in the case of PN junction diode. So let us see the connectivity of a forward bias, how it will be. Take your PN junction diode, anode and cathode, right? And with the help of a protective resistive element of around series arm element around 1 kilo ohm can be taken up. And if a P material of diode is connected to positive terminal of the battery and N material connected to negative terminal of the battery, this forms our PN junction diode, and this is the input voltage that is applied onto it. A DC source is connected, and by varying this particular DC source, we are going to see how the effect of diode impact onto the diode with respect to this forward and reverse bias we are going to see. And diode drop across the diode, we call it as forward, as it is under forward bias, and the current that is flowing through it, we call it as forward current. We are going to plot a graph between these two. So we are just trying to take up voltage drop across the diode, we represent it as VF, and current is represented as IF. So let us see when we apply this barrier, this DC voltage onto a PN junction diode, how the operation gets altered. As we have seen in the previous slide, that as and when you combine your P material and N material, there is a barrier formed which is having a potential of V gamma, and this particular potential, as we have already studied, for a germanium transistor it will be around 0.2 volts to 0.3 volts, and whereas if you take a silicon it will be around 0.5 to 0.6 or 0.7 volts. Right, this is how the barrier potential will be. Means in order to make the particles to move on, you have to apply a minimum of this so that it nullifies your depletion layer and current gets started. So now looking onto our PN junction diode when it is applied with a P forward bias onto it. So taking up the structural diagram of it in order to make the analysis. This is my structure of PN junction, which has a ions which is present on either sides, negative ions in P material, right, positive ions on the N material. And now I just try to apply a forward bias to it, positive to P and negative to N. All right, make a connectivity. This is our P material and this is our N, and this is how we have a barrier. Assume that the barrier potential V gamma is around 0.7 volts. Okay. Right. So now we shall just start applying our input voltage and check how it is present. Keenly observing the polarity of it, positive is connected to our negative ions which is onto the P side, and the negative is connected to the positive ions on the N side. So as we can see that rippling, that is opposite polarity, that has been connected with respect to the depletion layer polarity. As you try to increase the input voltage, Vi, as we try to increase, the ions which are present on either sides get neutralized. That is, they tend to get reduced. As I try to increase the 0.1 volt potential, respectively you're going to have a barrier potential getting reduced. That is, barrier gets neutralized and it reduces as we increase the forward bias. So this is a simple series arm resistor R we are trying to take, and as we apply a barrier potential of around 0.7 or 0.6 to 0.7, which is of silicon, if the silicon transistor has been taken up, we are going to have that all the depletion layer which is present on either sides get completely nullified, and you see that barrier is ready for the conduction of majority carriers. Once this depletion layer becomes completely zero, we'll see this. And now what is the thing that is present? We don't have any barrier. The particles, majority carriers on either sides are ready to move from one to that of another. Right? So here we have the majority carriers as holes, and here we have the majority carriers as electrons, and as the barrier has been neutralized, right, the majority carriers from N to P, P to N can move now. Since there is no barrier present, there is no force of repulsion for the particles, they can move. And here the current conduction or the particles will move because of the two reasons. One, we call it as diffusion because of the concentration difference, as we know. Diffusion is one reason because of which the particles start moving. The other reason because of which the current moves flows is because of drift. So diffusion is, as we can see, the concentration difference. P has majority carriers as holes and N has a majority carriers as electrons, and they can move from one region to that of another because of the concentration difference. The particle tend to get diffused. Holes will move from P to N, electrons will move from N to P. All right. And this is first concept of because of the charge carrier concentration difference that is present, diffusion. And the second reason for which the current flows is because of the drift. As we have connected P material with a positive terminal, so holes which are of positively charged deficiency particles are connected to positive. They tend to get repelled. As you increase your forward voltage, more amount of force acting onto it because of the force acting. Similarly on the other side also, negative terminal is connected to N material, so obviously electrons which are present will be repelled by it. So electron tend to move from N to P and hole will tend to move from P to N. So these are the two reasons. Drift is nothing but forcible movement of particles because of the potential, external potential that is connected to it. So with the help of which the particles start moving and the current will be constituted under forward bias condition. So till V gamma we see that almost the current is equal to 0, or during that time we have minority carriers crossing the junction. So because of which we have very small amount of current constituted, but once it crosses the barrier potential, once the applied voltage is more than barrier potentials, we see that the majority carriers are ready to move from one region to that of another because of drift and diffusion, which will try to constitute your forward current. So if I just try to plot the graph between these two, that is how your voltage across a PN junction diode is getting altered with respect to along with the current, that is that can be treated as a plot between VF versus IF. Forward voltage on x-axis, and we try to take a forward current in milliamperes. The current under forward bias condition is because of the majority carrier, so obviously it will be in the range of milliamperes. And now as we have seen that initially the current constituted is almost 0. Even we just try to increase the voltage, it will not. Once it reaches to the barrier potential of V gamma, depending on the diode that we take, the V gamma value will be. So till this point almost 0 current. And once the applied voltage is equal to the barrier potential and we try to apply more than it, the current increases with a reduced variation across the diode. So for us, across the diode we see that a drop is not much variation, but current rises rapidly because of the movement of majority carriers from P material, holes will move, from N material, electrons will move. This constitute your VI characteristics of a PN junction diode under forward bias. Under forward bias, as we observe that the current is because of the majority carriers. Similarly, we have another biasing condition. When we keenly observe the PN junction under forward bias, after V gamma, it is constituting the maximum current. So current will be in the range of milliamperes, and it's because of the majority carriers. The reverse bias condition is when we apply a P material with a negative terminal of the battery and N material applied with a positive, reverse to that of your forward connectivity when it has been done. That becomes your reverse bias condition. Here we go. This is your input voltage which is connected in the reverse mode, and voltage drop across the device is VR, and the current flowing through the device. As the polarity of supply is in the reverse, we see that your reverse current is going to be in the reverse fashion. So this is the connectivity of reverse bias, a PN junction diode, P material connected to negative terminal of battery and N material connected to positive terminal of the battery. So let us see how changes will occur in the PN junction diode with the help of a structure diagram. So this is my PN junction diode connected with a reverse bias. Okay, and as we know that initially when there is no biasing condition present, we see that ions are getting accommodated on either sides. Positive ions in N material, negative ions on p material. So which try to form your depletion layer, V gamma potential will be present. So here when we keenly observe, as we vary our input voltage, a reverse bias when it is getting altered. So respectively, what is the change that happens to the PN junction diode? Let us observe. As we have connected the negative terminal of the battery to p material, the ions cannot be nullified because of the negative potential connected to negative, but still the ions which are present in the other area of your P, which are not part of a depletion layer, will experience a repulsion force from the negative terminal. Negative terminal of the battery experiences or gives a force of repulsion onto it, because of which more and more ions which are present in the material, they tend to get accommodated towards your junction. And the same case is with the N material side as well. The ions which are not a part of your depletion layer, which are present on the other side, we tend to move because of the positive potential applied, force of repulsion. So more and more positive ions will be getting accommodated on either sides, which implies that more the ions will be getting accommodated on either sides. This is how its structure will be. Width of the depletion layer will get increased. And here when we keenly observe what is the charge carriers or how the current is constituted under this particular cases, as we know, depletion layer is also called as a barrier, since it doesn't allow the majority carriers. The current because of the majority carriers will be absolutely zero. And let us see the characteristics of a minority carriers in this case. And in P material, electrons are the minority, and N material, holes are the minority. So they cannot cross the junction. When we keenly observe it, electrons, we have a negative ions on this side, but on the other side there is a force of attraction that is present. Negative terminal connected to P material, so obviously electrons will experience a force of repulsion, and also there is a force of repulsion because of the ions which are present, but there is a force of attraction that is present on the other side of the depletion layer. So this is a force acting on the particle to push this side. Though there is a negative ions which are present over here, which is trying to push you back, push the particles back, but there is a force of attraction on the other side, because of which this the force from the barrier, from the supply which is applied, on also from the force of attraction from the other side of the barrier, because of which the minority carriers which are present in the material tend to cross the junction. So under reverse bias condition, or whenever the depletion layer is present, majority carriers cannot cross the junction, but minority carriers can cross the junction. So electrons which are present in P material, minority carriers will cross the junction. Similarly the case with the holes. Holes will move from N material to P material. So during this biasing condition, that is under reverse bias condition, minority carriers are crossing the junction, and as we know that minority carrier concentration is very few, the current constituted is also few. And as we know that electron movement is from P to N, that is P material has a minority of electrons. So electrons are moving from P to N, so convectional current will be from N to P. So under reverse bias condition, we see that the current constituted is in this direction. This is how you see the barrier potential exhibited, that is your polarity of the barrier, minus plus with the VR to be the voltage that is exhibited. So we are going to plot a reverse bias characteristics with the help of these two. Taking your VR, reverse voltage, on the x-axis and the reverse current on the y-axis. But here one point which we are trying to miss out is, in the previous case, whatever the polarity that we have connected, small minor change. So compared to the previous case, that is connectivity of forward bias, when it has been seen, we are trying to reverse the polarity of the battery. So in a plot, when we just try to look at it, the polarity of the supply has been reversed. So hence we are going to take the axis when we measure the voltage drop across the reverse bias also, PN junction diode also, we see that a negative potential will be exhibited. And also the current direction, previous to that of your forward current, the current direction over here has got reversed. So we try to plot our VI characteristics in the third quadrant. This is your reverse voltage, which is polarity has been reversed, and the respectively the current flows in the reverse direction. And as the current is because of the minority carriers, current will be in the range of microamperes or nanoamperes, depending on the doping and the material that has been taken up. So here also we see that as you increase the reverse voltage initially, as we increase it, the current across it initially it will be very small. Once the particles just move from one region, the particles start moving, then the current constituted will be. So linearly it start increasing as we increase the reverse voltage. And at one particular value of voltage, which we call it as breakdown, there will be a sudden rise in current. We call that point where the sudden variation that happens is called as breakdown voltage. And this breakdown voltage is because of the concept of breakdown mechanism that occurs in a PN junction diode. And as it is derived by a scientist called Avalanche, this breakdown is also called as Avalanche breakdown. And this particular topic of breakdown, we are going to study it detailedly in breakdown mechanisms topic. But as of now, let us briefly see what breakdown mechanism is. So when we are keenly observing the depletion layer width initially than to that of the reverse bias after applying a reverse bias variation is, the width of the depletion layer is increasing and the particle concentration is constant on either sides. The majority carriers which are present in P material is more, N material electrons are more. So on the carrier concentration is more on either sides of the depletion layer. But when we increase the reverse voltage, the depletion layer width is increasing because of more and more ions getting accommodated. So the space for the majority carriers which is present and also the minority carriers is reducing as the width of the depletion layer is. As the width is increasing, the space for the particles to move also it is getting decreased. So because of which there is a kinetic energy that will be acting on the particles because of the pressure that is, it's like a classroom in which if you accommodate 50 students, fine. If in the same classroom, if you try to push up 1,000 students in it, obviously the force of repulsion, that is congestion always occur. In the case of particles also, it's a force of repulsion gets started. So suddenly the half mv square, that is kinetic energy of the particles increases. So randomly at one particular point, there is always a threshold for everything. So till the certain value, you see that as the current increases, the voltage, as we increase the reverse voltage, current slightly increases, current constituted. But when the kinetic energy goes beyond to that of your barrier potential, once we apply barrier and more than it, the particle concentration increases because of the avalanche breakdown, and avalanche breakdown is because of the avalanche multiplication. As the concentration area for them is getting reduced, they tend to touch each other. Randomly they start moving, half mv square increases, kinetic energy increases, because of which they touch each other. Whenever they rupture each other, there will be a neutral atoms whose electron that is covalent bonds get broken out, and electron and hole pair will be created. So this is what we call it. This particle concentration is again increasing. They tend to again move because of the force of congestion that is present. So continuously this particle concentration increases, which implies that your particle concentration gets multiplied as we try to increase slightly beyond to it. That is what we call it as avalanche multiplication. They go on multiplying, because of which the breakdown occurs and the current increases, because the majority as well as minority carrier concentration is increasing. So your minority carrier current rises suddenly beyond when you try to apply more than it breakdown voltage. So this is a point where it has to be stopped, that beyond this reverse voltage there is a possibility of damage of the device as well. So this is how we have a PN junction diode applied with the forward and reverse. So let us combinedly take these two characteristics and plot our volt ampere characteristics, and here we are calling it as volt ampere since we are trying to take voltage on the x-axis, as we always call a VXY plot, right? X-axis we are trying to take a voltage, forward bias if it is VF, and the respective current is IF, which is in the range of milliamperes. And similarly, as we have plotted under reverse bias condition, we take a reverse voltage as the polarity has been reversed. Previously it was in plus minus polarity, the reverse minus plus polarity has been applied, so third quadrant, and as we have seen that current also gets moved, or current flow will get reversed, so your reverse saturation current, reverse current is in this manner. which is in the range of micro or nanoamperes. So we are going to combinedly call this plot. Voltage has a units of volts and current has a units of amperes. So VI characteristics can also be called as volt ampere characteristics. Combining your forward and reverse characteristics, this is how the structure would be. Till barrier potential, conduction is almost zero. Once the barrier is crossed, we see that current increases till V gamma. And under reverse bias condition, we see this is how the structure. Once the breakdown occurs, current suddenly rises. So till the breakdown mechanism, you see that the current increases, but once the breakdown occurs, avalanche multiplication happens, current suddenly rises to the maximum without much variation in the reverse voltage. So this is your VI characteristics or volt ampere characteristics of PN junction diode that is plotted under forward and reverse bias condition. And here we can just see that characteristic curve will be in this manner. Depending on how you are taking your PN junction diode, whether you are taking it under ideal case or under practical case, according to which the barrier potential and other parameters will be taken either infinity or zero, depending on the resistance has also been considered. So here when we keenly observe, the maximum current is conduction is happening from this point, that is V gamma. Before to it, the current is because of the minority carrier. So basic applications of a PN junction diode is it is used as a switch. Switch has obviously two states of it, on and off. So on means it's a closed path, maximum current conduction happens. So we consider our PN junction diode to be on after the barrier potential. Before to it, it is considered to be off. This is the practical scenario when it has been taken. Okay, diode is basically used as a switch, two conditions, on and off. When it is under forward bias and more than barrier potential when it is applied, it becomes your on state of a switch. The other case, it is off state of a switch. So this is how we have a PN junction diode and its VI characteristics that has been present. And moving on, how much amount of current is constituted? We are going to get this with the help of a diode current equation, which we write it in this manner, that is I, which is nothing but forward current that flows in a PN junction diode, is equal to I naught into e to the power of V by eta Vt minus 1. Alright, I is nothing but the forward current that flows in the PN junction diode, which we are trying to measure, and I naught is called as reverse saturation current. Alright, reverse saturation current, what it is I'll let you know. And V is nothing but the applied forward bias, as we are trying to define it for the forward bias condition, the maximum current constituted. If it is reverse bias, we are going to again represent V as a reverse voltage. And eta is a constant, which is taken to be 1 for germanium and 2 for silicon. Alright, 1 for germanium and 2 for silicon we are going to take up, and this particular eta value depends on what kind of doping that you do and what kind of environment where you are trying to use to your diode, depending on which this eta value will be. If it is a germanium diode, eta 1. For silicon, eta will be equal to 2. And this is the one, and we have one more factor called Vt, which we call it as volt equivalent of temperature. As we all know that there is always an effect of temperature on the material. We just keep a metal in sunlight. Obviously, it gets heated up, particle concentration increases, or accordingly, it will be variation will happen. So this voltage, the voltage equivalent of temperature. When you apply a temperature onto a PN junction diode, equivalently, there how much potential variation that occurs in a PN junction diode is studied by this volt equivalent of temperature. Vt is called as volt equivalent of temperature. And this particular formula is given as kT by Q. When we substitute Boltzmann constant and charge of an electron, this comes out to be T by 11,600. And do mind, this is taken in degrees Kelvin. Temperature should be taken in degrees Kelvin. By substituting your Boltzmann constant and charge of it, we land up with the equation of Vt as T by 11,600. So this is our diode current equation. Shockley, as it is given by him, it is named after him as Shockley equation. I is equal to I naught into e to the power of V by eta Vt minus 1. Exponentially, the current curve is getting raised. And what is this reverse saturation current is? Under reverse bias condition, the maximum current that is constituted by the device before to that of breakdown, this current we label it as reverse saturation current I naught. Maximum current that is constituted by a PN junction diode under reverse bias condition, we call it as reverse, as the diode is under reverse bias, and maximum current constituted, so hence we are calling it as saturation, so I naught is called as reverse saturation current. So this is the diode current equation, amount of current constituted, and here we shall just try to see what is the effect of temperature on a PN junction diode and respectively its effect on the volt ampere characteristics. As we know that as the current gets temperature gets raised, so there will be a rise in temperature. It's nothing but a heat energy supplied to the PN junction diode. Heat energy, when it is supplied, obviously the neutral atoms or the covalent bonds which are present gets in energy, they get broken down, so electron hole pairs will be created. So carrier concentration increases as the temperature increases, so which implies that the impact of temperature on the current is present. Carrier concentration, when it is increasing, obviously the current also gets increased. But when we keenly observe the temperature effect onto the current, we have a majority carrier current I present, and also we have a minority carrier current, reverse saturation current present. As we have seen, under reverse bias we have the minority carrier current, under forward bias we have a majority carrier current, and this particular I and I naught, impact of temperature on I and I naught when it is keenly observed, assume that some x degrees centigrade temperature has got raised. Because of this particle temperature raise that is present, 10 covalent bonds are getting broken down. Right? 10 covalent bonds which are present are getting broken down. So when 10 covalent bonds are getting broken down, 10 electrons and 10 holes will be created. Assume I'm trying to define it for a material of N type. N type electrons are the majority carriers which constitute your current I, and minority carriers are holes which constitute your reverse saturation current I naught. So for every x degrees centigrade, 10 covalent bonds are getting broken down. As we know that majority carrier concentration is high compared to that of minority, assume that my device defaultly has an electron concentration of 1000. Okay, majority carriers, the N material, and the minority carrier concentration is 10 without raising temperature, before raising the temperature. So because of the covalent bonds, 10 electrons have formed and 10 holes are getting formed, right? So 10 electrons and 10 holes are getting formed. So for the basic concentration of 1000 particles, we're going to have 10 electrons getting added up, but the basic particles of hole is 10 and 10 holes are getting added up, which implies that impact of the temperature is less. 1000 particles getting added up with 10 doesn't make much difference, but whereas 10 particles getting added up, the current is getting doubled over here, which implies that impact of temperature is more on the reverse saturation current than on the forward current or the majority carrier current that is present. So impact will be more on I naught, and it is experimentally derived that for every 1 degree centigrade raise in temperature of a semiconductor material or a PN junction diode, there will be a raise in your reverse saturation current by 7%. For every 1 degree centigrade raise in temperature, there is an increment of 7% in the reverse saturation current, and for so on. When we try to raise 2 degrees centigrade, it becomes your, if 1 milliampere of current is flowing and I raise 1 degree, it becomes 1.07 milliamperes, and so on. As I try to raise, for every 10 degrees centigrade, it is found that it is almost comes around, the raise will be almost coming around it. It becomes almost 1.9 8 factor, which is taken to be 2. So when we keenly observe, at some temperature it was 1 milli, after 10 degrees rise in temperature it's 2 milli. From this conclusions it can be stated that for every 10 degrees centigrade rise in temperature, the reverse saturation current gets doubled. So based on this, a relation is also been given, variation in the reverse saturation current, which can be given as at temperature T2. T1 temperature, we have a reverse saturation current if it is I01, and at T2 temperature rise, when it is taking up, the reverse saturation current is defined as I02. So the relation between I02 and I01 can be given as I02 is equal to I01 into 2 to the power of T2 minus T1 by 10. Okay, as it is getting doubled for every 10 degrees. If T2 minus T1 is 10, the difference is 10. So this becomes 1, 2 times I01. So it is tallying the condition that for every 10 degrees centigrade rise in temperature, there will be an increase in reverse saturation current and it gets doubled. Alright, the percentage variation is for every 1 degree centigrade, 7% increment will taken. For every 10 degree centigrade, the reverse saturation current gets doubled. So this is the impact of reverse saturation, reverse onto the reverse saturation current. Similarly, we have an impact on the voltage as well, the potential difference as well. The variation is for every 1 degree centigrade rise in temperature, there will be a decrement of your forward voltage, or your biasing voltage drop across the diode decreases. And what is the decrement level of the voltages? It's around 2.5 millivolts. Per every 1 degree centigrade rise in temperature, there will be a decrement, so we represent it as minus. It is taken as minus 2.5 millivolts. Okay. As the temperature increases, reverse saturation current gets increased, but as the temperature decreases, the voltage increases, the voltage drop across the device reduces. So this can be visualized with the help of this graph, as you can just keenly observe the effect of temperature onto the VI characteristics, volt ampere characteristics. As you can see, this is a blue line that has been drawn at a room temperature of 25 degrees centigrade, right? As we try to increase the voltage to 125 degrees temperature from 1 to 125 degrees centigrade, the dotted line is black dotted line, thick dotted line has been shown, which implies that as you try to increase the temperature from 25 degrees to 125, the barrier potential is getting reduced, so potential reduces. As you decrease, minus 75 degrees centigrade, it is another one that has been taken up, so it will try to increase your barrier potential. Respectively, you can see the reverse saturation current impact as well, I0 variation. The blue line is at a room temperature of 25 degrees centigrade. As we increase the temperature to 125 degrees centigrade, the current reverse saturation current has increased a lot. And as we decrease the temperature to minus 75 degrees, the reverse saturation current becomes almost zero. So this is how we have the impact of temperature on the VI characteristics. Reverse saturation current increases with temperature, whereas the drop across the PN junction diode decreases as the temperature increases. So this is about our topic of VI characteristics of PN junction diode and effect of temperature on it. That's all for our lecture 2. Thank you.